We're doing the 1994 AP problem today. I'm going to be doing part A and B. Now, the question reads, a thin non-conducting rod that carries a uniform charge of length lambda is bent into a circle of radius r. So, express your answer in terms of lambda, r, and fundamental constants. So, now part A asks, so determine the electric potential V at the center of the circle. So, as we know, V, the formula, is equal to 1 over 4 pi epsilon naught times the integral of dq over r. So, now obviously we can evaluate this simple integral to simplify it. So, this will turn out to be 1 over 4 pi epsilon naught 2 over r. But, so now we are given that this rod has a uniform charge per unit length of lambda. So we know that Q is equal to lambda L, and L will represent the length of the rod. So if we can also find out that L by taking the circumference of the circle, because it's wrapped around the whole circumference. So if we take the circumference, it will be 2 pi r. So L, the length, is equal to 2 pi r. So if we substitute back that in, so Q will be equal to lambda 2 pi r. So now if we substitute Q back into the original expression for potential, we should get potential equal to 1 over 4 pi epsilon naught lambda 2 pi r over r. And now, if we take everything and we cancel it out, what we should eventually end up is so 2 and 4 cancel out, so this will be left with the 2. The pi cancel out, and the r cancel out. So eventually the numerator should be lambda over 2 epsilon naught. So this was it for part A. Now part B asks for the magnitude of the electric field E at the center of the circle C. So if we were to draw an electric field diagram, it would look something like this, like where the electric field lines are going out from the center of the circle. And what happens is, since the point is acting for at the center of the circle, and it's equidistant from all points of the rod, so all the electric field lines will eventually cancel out. So what ends up happening is, the electric field is in fact at the center of the circle, C is 0. So that's it for part B.
Okay, so part C is about a thin non-conducting rod that has a total charge of Q and a total arc length of L. Hope you can see that. And the angle of the arc that's created is 2 theta. Okay, evenly, theta and theta here. So C is we have to determine the total charge on the rod. Apparently, we have lambda already given to us, so lambda equals total charge over total length. It's Q over L. And we rearrange the equation to get Q equals lambda L. So now we have everything except we have to find L now. So L is basically circumference times the angle that creates the arc, basically. So that would be 2 theta over 2 pi, because there's 2 pi radians in a unit circle. That's the fraction of the angle. So we can cancel out the 2's. And L is circumference, we know is 2 pi r. That's just 2 pi capital R times theta over pi. We can cancel out the pi's, and we get 2r theta for the length. Now we have to find Q. That's the problem. So Q is lambda L, which is lambda times 2R theta. Yields 2 lambda R theta. And that's your answer for the total charge. Part D. Okay, hold on. So for part D, now that we have the total charge of the arc, the arc rod, we have to find the electric potential at the center of curvature C of the arc. So basically, potential is, formula for potential is 1 over 4 pi epsilon naught, which is equal to K. You can write it either way you want. Integral of dq over r, the radius of the circle, the arc. But you know integration is like the sum of infinite parts, so we easily immediately get 1 over 4 pi epsilon times q, the total charge over the radius. So we just have to substitute q in because we already got q from part C of the rod. So that would be 1 over 4 pi epsilon times 2 lambda r theta over r. And yes, the r's cancel out, so this is your final answer. 1 over 4 pi epsilon times 2r theta. But we're not even done yet, because we have to cancel out this. We have to simplify the fractions. And that will give us lambda theta over 2 pi epsilon. And that is your voltage, your electric potential for that arc.
This is part E. It asks for the magnitude of the electric field for this diagram. First we'll find the direction of the electric field. In the the y components all cancel out because it's symmetric with respect to the y-axis. In the x-axis, there's going to be components, they're all going to go this way. So the electric field is going to be this way because this, say we did it here, there's going to be an x component that way and a y component downwards. And here there's going to be another x component this way, but the y component is going to be in the opposite direction. So these two are going to cancel out, but these two will keep on adding to each other. So the electric field will be in that way. Now to find the electric field, we can't use Gauss's law because there's too many components to deal with, and this is not a good surface to do that with. So we're going to use the original traditional way. E equals integral of dE, and dE we know is equal to 1 over 4 pi epsilon naught q over r squared. dq over r squared. So we just plug this in here. E equals integral of 1 over 4 pi epsilon naught dq over r squared. And now we have to use this this relation again, using the charge density. So let's just do it here. Q equals lambda L, and L equals r d theta. Here, actually it equals r theta. We showed that in the previous section. And if we take the derivative of both sides, dl equals r d theta. And if we take derivative here, dq equals lambda dl. So I'm just taking the derivative so that you can get for each minuscule, infinitesimally small dq, dl, and d theta. Okay, so now we can substitute this value in of dl into here. So dq is going to equal lambda r d theta. And now we can substitute this into here. So E equals integral of 1 over 4 pi epsilon naught dq, which is lambda r d theta over r squared. That's total E. This is E including the x component and the y component. Okay, I'll take it all the constants now, which is basically, all of these are constants because d theta means with anything with respect to theta you take the integral of. But nothing here is with respect to theta, so we can take the whole thing out. So it's 1 over 4 pi epsilon naught lambda, and we can simplify this 1 over r times the integral of d theta. This is equal to E. But we said previously that the y component doesn't matter, so when we're calculating E, we only need the x component. So we can just take EX, which would be cosine theta times E, right? Because the angle here is okay. So we have basically a triangle. This is the angle. We want the x component, so we take the cosine, and this is the total E. So this is E. This would be EX. So it would be EX times cosine theta equals E. So EX equals 1 over 4 pi epsilon naught lambda 1 over r times integral of cosine d theta. Cosine theta d theta. And the limits are going to be from negative theta to theta because you're starting from here and going this way or you're going this way. It doesn't matter. So it's negative theta to theta. Now we just take the integral. The integral of sine theta is, integral of cosine theta is sine theta. So EX, I'll do it here. EX equals 1 over 4 pi epsilon naught lambda times 1 over r times sine of theta minus sine of negative theta. This is what I did right now. I just took the integral and evaluated it at the limits, theta and negative theta. Now this is where some trigonometry comes in. If you remember from, I don't know, whenever we did trigonometry, sine of negative theta is an odd function, or sine of theta is an odd function, so sine of negative theta equals negative sine theta. Right, so basically what I'm saying is sine negative theta equals negative sine theta. So if we substitute this back in here, we get our final answer of 1 over 4 pi epsilon naught lambda times 1 over r times 2 sine theta. And we can simplify this, yeah, but that's basically it.